Hey, welcome back. So now we're going to see that a lot of the things I told you earlier are actually not quite legitimate. And in fact, the octet rule, it turns out, is only an approximation. And why is that? Well, if you are a second period element and you ask yourselves, where can I put my electrons? Then you can put them in the S or the P subshells, and that gives you a total of 8. So that is the octet rule. And the problem is that if you're on the third period, right, I think I may have mentioned you can put them in the 3s and the 3p, right, but there's also another orbital, the 3d, and you can actually hold up to 10 electrons in the 3d. So that gives you a maximum capacity of 18 electrons. So in fact, in Advanced Inorganic, you might learn about the 18 electron rule, but let me go ahead and show you an example of a substance where we have to actually keep that in mind. So for instance, I can take something like xenon difluoride, and you might say, wait a minute, right? Xenon, I know doesn't react, it's a noble gas. Well, fluorine is incredibly electronegative, and xenon's so fat, it's so big, that the fluorine can literally take its valence electrons and use them to make bonds with. So let's go ahead and suspend our disbelief here and calculate the Lewis structure. Xenon's in group 8, fluorine's in group 7. There's 2 of them, so that's 14 plus 8. That's 22 electrons. Gosh, I tell you, mental math is really tough on me sometimes. We can draw a structure. We put the xenon in the center, the fluorine on the outside, electronegative atoms go on the outside, the lower electronegativity ones on the inside, and that uses up a total of 4 electrons, giving us 18 left. And we complete the octets on the outside, so 1, 2, 3, 4, 5, 6, it gets us up to 8. That is 12 electrons, leaving 6. The 6 electrons, they go on the center atom, and they always go in pairs. And notice this is kind of a little bit busy here. Well, it is busy because you've got a total of 6 electrons there in lone pairs, and 2 and 2. You've got a total of 10 electrons around that center atom, right? So that should freak you out. But for the fact that we are allowed to expand octets, if you are a third period element or beyond, right, to infinity and beyond. So you get those d-orbitals that can hold electrons, and you can actually hold up to 18. So that is actually a perfectly valid Lewis structure. Although it looks weird, it is totally cool. So let's go ahead and look at another example. So there's a wonderful gas actually that's pretty stable, that's sulfur hexafluoride, and we can calculate its Lewis structure. Sulfur's in group 6. And fluorine is in group 7, and let's see, that's 48 electrons, I hope. And if we go ahead and we write its Lewis structure out, then we're going to go ahead and, oh my gosh, right, we're going to take sulfur in the center, and all those very electronegative atoms go on the outside, and you're like, holy cow, right, that is massive. So my electron count, 48, and I'm using up 2 for each bond, so 6 bonds is a total of 12 electrons used up. That's 36 valence electrons left. And I'm going to complete the octet on the outer atoms. Fluorine is second period, right? It can expand its octet. It doesn't have 2d orbitals. So, holy cow, bunga, right? So that is 6 times 1, 2, 3, 4, 5, 6. That's 36 electrons I've just used up. So that actually gives me no electrons left. And if I look at that center atom there, you can see it's got 2, 4, 6, 8, 10, 12 electrons around it, right? So don't let that freak you out. Right, it's got 12 electrons. That is actually fine. Why is it fine? Well, sulfur is in or beyond the third period, and so it has access to those d orbitals, so it can actually hold up to 18 electrons. So as long as I didn't go over 18, I would actually consider that to be a perfectly valid structure.